Hi, I'm George Woodbury from College of the Sequoias in Visalia, California, and in this video, this is the first of 6 videos where we do some applied problems involving exponential or logarithmic functions. So we're going to begin with the exponential growth and decay model, which is given by this formula, y equals y sub 0 e to the kt power. Now y sub 0, or y naught, is the amount that's present initially, and k is a constant. And to model the function, we need to figure out what k is, and to do that, we'll be given a pair of data besides y sub 0 that we can plug in for y and t, and then we can find k. And we'll round k to 6 places as a rule. Then we can use it to solve any other problems like 1b and 1c on this handout. So first, let's read the problem. In 1974, the total world population reached 4 billion people. In 1999, the population reached 6 billion people. Find an exponential function that gives the world population in billions, where t is the number of years after 1974. So 1974 is our beginning year, year 0 in this problem. I'm going to copy down the variables in the formula. Y sub 0 is the initial population. That is the 4 billion. And we'll just have to remember that even though I write 4, that represents billion, so 4 billion. In 1999, it reached 6 billion, and that was 25 years after 1974. So we can use that data to find the value for k by substituting into that formula. So y equals y sub 0 e to the kt power. 6 equals 4 e to the k times 25 power. Putting in 25 for the number of years, 6 for the new population, and 4 for the original. Now we need to solve for k, and we begin by dividing both sides of the equation by 4. Fortunately, 6 divided by 4 is a decimal we know, 1.5. You could leave it, though, as a fraction. In later problems, you will. So I'm going to keep working it with a fraction, but here you should really change that to 1.5. So 6/4 equals e to the k times 25 power. Now we'll take the natural logarithm of both sides of this equation, and we have the natural logarithm, the natural logarithm of 6/4 equals the natural logarithm of e to some power is just that power. So this is, not 6/4, k times 25. Now we can finish by dividing both sides by 25 and going to our calculator to approximate this. So k equals the natural log of 6 divided by 4, all divided by 25. And let's go to the calculator. Function ln, back to the main, inside the parentheses, I'm going to type 6 divided by 4. Tap outside the parentheses, divided by 25, and there is our value of k, 0.016218. The next digit's a 6, so that means we're going to round this up, 0.016219. Now that's what we need to start the problem. Now we can actually solve problems based on this model. So again, the model is y equals 4e to the 0.016219 t. That is the model. Use the function to predict the world population in 2047. So I'm going to make the same table, y sub 0, k, and t, and I'm going to put in the 2 values that I know. And 2047, that's a measure of time. 2047 minus 1974, that is 73 years. And so what we don't know is the value of y. Let's find that. Y equals 4e to the 0.016219 times t power, I can put in those values, that value of t that we just found, y equals 4e to the 0.016219 times 73 power. And here we're looking for a population, we'll round this to the nearest tenth of a billion. On the next line, 4 times function e to the x, and our exponent was, in parentheses, back on the main screen, 0.016219 times 73. And when we press enter, we get 13.069. That rounds to be 13.1 billion. In the year 2047. Now I've got one more problem where this time we will know the population we're trying to get to, and we'll be able to figure out what year that will happen. I'm going to copy down the model one more time. Y equals y sub 0 e to the 0.016219 times t power. And here, the 11.5 billion, that's our value of y. Oh, and I'm sorry, I meant to put in 4 for the value of y sub 0, because that is our initial population. That's why I think it's still better if you list all the variables rather than copying down the model. We know the initial is still 4. We know the value of k is still 0.016219. And now my value of y is 11.5. I need to find t. And that way I can get everything into the formula the right way. All right, to solve this, we want to isolate the exponential expression, divide both sides by 4. Now again, 11.5 divided by 4 is one you could do with a decimal value, but I'm going to continue to leave it in fraction form so I can show you how to handle that in the calculator. Equals e to the 0.016219 times t power. Take the natural logarithm of both sides of the equation. On the left-hand side, we just have the natural log of 11.5 divided by 4, whatever that is. On the right-hand side, natural log of e leaves us with just the exponent, 0.016219 times t. And now we can divide over that value of k, 0.016219. And now we can go to the calculator to finish that one. There we go, by the magic of delayed iPad. One thing that I want you to notice is that there's kind of a pattern here. What we really have is the natural log of y divided by y sub 0. It's the ratio of those two. And then that's all divided by that constant k. So once you find that value of k, we can head here whenever we're trying to solve for time. Little shortcut. Anyway, let's go to the calculator. Function natural log, back on the main in the parentheses, that's 11.5 divided by 4. Tap outside the parentheses, divided by, now we want to use that value of k again, 0.016219. And we get 65.1. We were looking for the time, we're looking for a year, so I'm going to round that to the nearest year, 65 years. And we do need to add that to our starting year. 1974 plus 65 is 2039. Come back in 2039 and let me know how we did. That's it for this one. We'll move on to a different type of problem in the next video. But again, remember, the strategy that we used here, we try to find the model first, and we use an initial, we use an initial value, y sub 0, and then we use a second value and a second amount of time to figure out what k is. Then once we know k, we can use that model to solve for either y or t. If we're given half of that pair, we can find the other half.